We're in the final straight. We're on quite a tight schedule. There are folks who various buses have to leave at various times, and we had to rearrange the schedule a couple of times just to accommodate folks' departure needs and so on. But we're going to begin immediately with Rene Hoet, who's the Chief Innovations Officer at Fair Journey, and he's going to speak on novel antibody technologies for future therapeutics. Rene.
Thanks. Thanks a lot, Dennis, for the kind introduction, and thanks all of you. Actually, after this huge party yesterday, managed to come here on time and listen to the talk. I basically would like to talk about novel antibody technologies, which we are developing at Fair Journey. A very short introduction to Fair Journey. Then I will talk about one of those new technologies, this new Explorer library, which is a modular antibody library, and how we apply actually this phage and mammalian display to select antibodies for developability. And then I will finish with some of our thoughts on new antibody technologies which we want to develop in the next year in Fair Journey. So Fair Journey Biologics is basically rooted from, let's say, the AppLinks technology using VHHs. So there's a lot of knowledge on VHHs, but we actually have now expanded this to all type of antibody formats. So we use phage display as our core technology, and basically in this more than 10 years now, 11 years, we actually, from the work from Fair Journey, there's at least 14 antibodies in the clinic. So we support our clients just really from the stage from early target validation to really the final cell line development. So discovery, the engineering, the production of antibodies at all scales, small and large scale, but also for antigens, functional activity, developability, very important feature, early and late developability, and the stable cell line development. And on top of it, we have a storage and logistics so that you can actually send your samples basically throughout the world to other parties. So then, the technologies we have in Fair Journey, they're all display technologies, antibody display technologies, using phage display as the core technology, using antibody libraries from human donors and llamas, non-immune libraries, Fab fragments, single-chain fragments, and single-domain antibodies, but also use immunization, all different species, llama, chicken, mice, rat, and rabbits, and actually make immune libraries from that and select actually antibodies. And we also actually then have the capabilities to humanize all these antibodies, so deliver fully humanized antibodies to you. Basically what I'm going to talk today is a new antibody library which is made in the company, which is actually made out of diversity from human donors, but also synthetically designed on the millions of sequences. The Explorer library, which uses actually phage display and mammalian display as a platform. So what is this Explorer library? So the Explorer library is actually based on selected stable heavy and light chain scaffolds that are frequently used in humans. It includes actually most frequently used heavy and light chains. And also it actually, we look for the ones that we actually see curing in our phage display libraries. Well expressed in bacteria and mammalian cells, and very importantly, also used in clinically approved antibodies. So how do we introduce the diversity? That's sort of illustrated here. We actually take from the hundreds of millions of sequences, we design actually the CDR1 and 2 for the heavy chains and the CDR1, 2, and 3 for the light chains. We basically design based on the human repertoire. So we mimic basically with synthetic design basically in humans. The CDR3 of the heavy chain we take from human donors because it's almost impossible to design from 4 to over 30 amino acids and almost a completely random sequence. So we take this from donors. And we put in the design all the features to reduce the biophysical liabilities. Try to, for example, avoid glycosylation and deamidation. So this large human phage library is then used for selection. And then because of the module system, we can actually then finally optimize this in mammalian display. So this is the type of modules we made, basically. So CDR1-2 synthetic, CDR3 of the heavy chain from donors, and then the light chains and CDR1, 2, and 3. We made then all these different sub-libraries, and we focus, of course, putting most of the diversity to the CDR3 of the heavy chain, because that's the most diverse element. And we put this together in a library, which is basically over 10 to the 10. The total diversity of all these elements together is 10 to the 27. So we can use this 10 to the 27 to model and shuffle to finally optimize our lead antibodies. So then the library was made, and we checked the diversity. Nowadays, of course, we can do this easily with NGS, and sort of for the VH1 and 3 family, and lambda and kappa antibodies. Each about 500,000 sequences were analyzed, and we see a huge diversity here. Here you see the diversity in CDR1, 2, and 3 of those different elements. Also, I think we actually selected for really read-through, so that there was no artifacts or any stop codons, which used to be in these, let's say, in the historic old antibody libraries, and we avoided all these things. VH3 and the CDR3 is typically distribution, what we see with an average length of 13. And then, of course, NGS allows you to really look really deep in the diversity. Here's just an illustration of the VH3 family, which is basically sequenced over 500,000 antibodies, and you see that over 520,000 antibodies are really unique and seen in one cluster. So they occur only once in the library, and here you see that there's a limited number of antibodies that occur more than once in the library. So then you can look a little bit deeper, and this gives you a flavor of how the design is made. If you focus, for example, here on the CDR3 of a VH146, you can see that some amino acids we kept constant. Here the tyrosine in position 2, the methionine in position 4, really because also in human repertoires, these ones are constant. And this is important, you know. In the old days, you used to people randomize things, and that actually is destroying the structure of antibodies. So we keep on the other position, we keep the germline residue basically in most of the cases, and then we put, depending on the sequence diversity in the databases, we put either 18 or 16 or 15 amino acids. Also try to avoid all these biophysical liabilities in the design. So this is we put maximum in total 2 amino acid mutations per CDR, both in CDR1 and CDR2. And therefore, you see that the germline residue is overrepresented at every position. But still, every antibody has 2 amino acid mutations, CDR1, mutation 2 in CDR2, etc. Similarly, for the light chain, also there, we used the same type of design and introduced the diversity in the library. So then we also compared the NGS data of the library to a database of all clinical, so let's say most of the clinical antibodies, 498 antibodies. And you can see that if you look at the average biophysical liabilities of heavy and light chain here, compared the Explorer to the clinical antibodies, we're doing pretty good. So these are not selected yet. So this is just the total library without any selection. Here's the average for the heavy chain, average for the kappa light chain, and average for the lambda light chain. They all are similar except for the lambda. There's about 74 antibodies now against the lambda, with the lambda light chain in clinical trial. And you see that actually the Explorer performs pretty good compared to the antibodies in the clinic. These are the biophysical liabilities which we include in our analysis. So then, of course, we started really looking in a simple validation on the phage library. We typically see a high number of antibodies. We took their PD1 and HER2 as basically, let's say, model targets to do a selection on. 3 rounds of selection in solution, and then screened about 900 clones for binders. And these are just off rates of some of these antibodies. Looking at diversity of these antibodies, you can see that we look at cluster size. That means how many unique antibodies are there in the selection. after 3 rounds, and you see that the majority of antibodies occur only once after 3 rounds of selection, and there's this, so that means that diversity is probably underrepresented yet in the analysis, and there's many more antibodies in the library. In the case of PD-1, you find that majority uses VH1 family scaffolds, and in case of the HER2, you see actually a distribution over also VH3. Actually, all the different scaffolds are used. Length distribution, quite variable between 4 and over 35 amino acids. And here the most important thing, how is diversity actually, and you see that the diversity both for PD-1 and for HER2 is distributed over all the different CDRs of the heavy chain, and also similarly, this is true for the light chain. Due to time, I can't show those data, but basically you have to believe me that also the light chain is really diverse. So one of the additional features we have built in the Explorer library is that we can screen very quickly, very early in the process for functional activity as IgGs. And typically, this is what you normally would do in a classical workflow with single chain or FAPS or any format. So you start with the library, you select basically on the target, then you screen for the soluble materials, FAPS or single chains. You look at the unique clones, which have a functional activity, and then you actually and then you convert to IgG. So very late in the process, you go to IgG. And for some activities, for example, if you're looking for agonistic activity, it's very difficult to determine really early on which antibodies are the interesting ones. It's not only affinity which matters. And therefore, I think it is really an advantage that we can do actually very early in the process from the single chain, just after the screening, or as a soluble FAP, you can directly go to IgG. So instead of testing now, let's say 10 to 20 to 96 IgGs, you can actually test thousands of IgGs early in the process. So we have an efficient IgG batch reformatting put in place, which actually can then screen for, if there's a small amount of IgG produced, 1 to 5 microgram, you can screen directly for biologic activity. So why is it important? We can really directly early on look for biologic activity. It's a faster discovery process. You know very early on, actually, if you have the biological activity that you desire. And it allows testing really in the desired therapeutic format. So the other format we have built in is actually that because we have these scaffolds, these modules, there are basically individual libraries, and we have DNA in the freezer of all these modules. Once we actually select antibodies, for example, to the PD-1 or HER2, we can actually shuffle CDL1, 2, or a light chain library very easily in it. The DNA is ready, clone it into select on phage, and then move to mammalian display. That allows actually to select not just for improved affinity and potency, but also directly for developability. So improved developability using our mammalian display technology. And I would like to show you a bit more why we think mammalian display technology is really important. And if you think about designing an antibody and with a certain target product profile, we are very good with the display technologies to get antibodies with the right affinity, specificity, and also actually, although a bit difficult, function. What we're actually bad in phage display is actually to select the ones that are developable and have the right properties to become a drug. And that's actually the power of mammalian display. Mammalian display, you can screen tens of millions of clones. You get directly information of expression level and affinity. And I think the big advantage is you can work in IgG directly or any other format. For example, bispecific CAR-Ts, VHHs, or TCRs. And actually, you can screen directly in the production cell line type. So we use standard HEC293 cells for that, but we also set it up for CHO cells and for example, Jurkat cells. And you have a potential for functional selection. So the challenge of mammalian display is actually that to get really only one copy per gene integrated, so there is a linkage then between the genotype and phenotype. And the solution actually, which was basically developed, was using a homologous recombination assisted by nucleases, tail nucleases. It's actually shown over here. So basically, in the module, which is we actually clone the antibodies or antibody repertoires under a promoter of two promoters for the light chain and heavy chain. Under control of the blastid siding, which is without promoter, there's then an overhang left and right, which is site in an intron sequence of the ARVS gene. So then upon recombination in the genome, this is then integrated, selected for 2 weeks on blastocidin, and about 1 to 3% shows actually stable integration then in the genome. And then you actually can select the antibodies for display. This heavy chain is then linked to a PGF receptor gene, so that you can actually then have that display of the heavy chain on the surface, and the light chain is linked. So you have the antibody displayed on the surface of the mammalian cells. So what can you do with mammalian display? You can select and improve antibodies, but in principle you can also do this with phage display. The power of mammalian display is you can select for optimal biophysical liabilities, and this is sort of shown here on a published case study with bocacuzumab, an antibody developed by Pfizer to PCSK9, and this antibody failed in phase 3 clinical trial because of significant immunogenicity. So it came actually, this antibody, from a mouse hybridoma, which was humanized, and after humanization, phage display was used to improve the antibody from 300 picomolar to 5 picomolar. And by doing this, actually was analyzed by Jane and al. In a paper that actually this came with several red flags for developability. And indeed, if we actually display bocacuzumab and the original antibody on mammalian cells, HEX cells, you can see that bocacuzumab displays actually pretty poorly compared to the original antibody, which was not affinity matured. So the question is, can we actually fix then bocacuzumab using this mammalian display? And the answer is yes. And the way this is done actually is by making a limited number of mutations in the CDRs of bocacuzumab, making a library of about 10 to the 7 of that, and then selecting actually for target binding, PCSK9, as well as expression of SC. So you select the population here in the red quadrant, which actually is actually binding well, and also actually expresses well on the surface of mammalian cells. So then actually you can actually sequence all the unique clones and do an IgG screening which ones are binding. In this case, there were only a very limited number of clones analyzed, 88 different ones, and all 88 actually showed better developability than bocacuzumab. Here there are just 3 shown here, 3 variants, which actually, by the way, only have 2 amino acid mutations versus bocacuzumab. And you see dramatic decrease in the polyreactivity here of these clones compared to bocacuzumab. Also, expression level actually goes up threefold here for the antibodies from 70 to almost 200 milligram per liter. Diffuse light scattering is actually improved. And AC-Synth, which is a method developed by Peter Tessier, which looks really at a very high concentration of antibody on magnetic beads, is really also improved. So all the properties of these antibodies are improved by using mammalian display. So in summary, mammalian display is a unique platform to track actually clinical candidates, screening tens of millions of clones. And you can, the beauty of it is you can screen directly in the final therapeutic format. This could be a regular IgG, but this could also be a bispecific. And you can actually, this allows also to fix broken antibodies, but also we use it, of course, to select immediately the ones that are developable. So this is another case study where actually there's more than, let's say, a pool of over 110 CMC stage biologics assembled. So they're all clones in the mammalian system. And this is a collaboration with a large pharma partner, and they had all the developability data from all these 110 antibodies. And then they were selected using mammalian display. They recognize all different targets, and they're all different formats, by the way, as well, not just the regular IgGs. If you then select for low display, medium, and high, and you rank them, you can see that the ones that are high display here, they actually have also the lowest score for self-association And this is a kind of, these measures are a combination of different developability assays. You can also actually show it in a different way, in different classes. Class 1 is actually the best antibodies with a score of 0. They're mostly here. Class 2, they have some liabilities. And then class 3, which are basically the poor ones, which are in input as well as in the low displaying one. So mammalian display is a very good reporter for the self-association in late-stage development. So you can ask the question, why is that so good? It's too good to be true. You know, it's more or less the same as why I thought yesterday with AI. It's too good to be true, but still, it could be. And one of the things which was looked in early on was to compare actually mammalian display with yeast display. Yeast display is also reported to actually select antibodies for good developability. And when we did this comparison, we took two antibodies, one against ANH1 and the other MEDI1912, which is a VEGF antibody. And from those antibodies, there is a parental antibody, which actually has poor biophysical properties. And then there is an improved one, which only differs a few amino acids, which actually has much better developability properties. And you can see there's about 2 log shifts in flow cytometry in the mammalian display with 2 doses antibodies. If you put the same antibodies with the same sequences in mammalian display with an IgG expression, you see there is some discrimination, but it's much poorer than with mammalian display. We think this has to do with the fact that yeast has a cell wall, and in mammalian cells we have actually just a membrane which we can select on. So what do we think is the mechanism which actually shows this superior developability? And we think it's actually a combination of productivity, you know, how quickly and how much goes to the surface of the antibody, depending on expression, TM, ER processing, and how much actually, and then the ones that are on the surface, do they stay there, or actually, if they self-associate or aggregate, they actually internalize and degrade it. So it's and for a long time, actually, this was just a hypothesis. But this year, actually, there was a publication in Nature Communication from a group from David Paul and co-authors, and they actually showed for a HER2 antibody that it's indeed endocytosis which is playing a role in mammalian cells to degrade actually antibodies that don't form properly. So we did an experiment in our mammalian display system where we took the same MEDI1912 antibody, the one actually that, the original one, parental, that displays relatively poorly, and the improved one actually that displayed about 100-fold better on our mammalian cells. So if we now add a blocker for endocytosis and degradation, cytochalasin D, and we then do the incubation, you see that there is the same display of the improved one and the parental one. So the parental one is actually now, because there's no endocytosis and degradation, actually the same way. So we think that endocytosis and internalization is a really major mechanism which actually makes that you can select antibodies for developability using our mammalian display system. So is it only true for IgGs? And the answer is that we think no, because also VHH fragments without an FC or with an FC, you can actually discriminate using our system with poor VHHs versus good. The good ones are displaying much better. Same is true for bispecific, and I think that's an interesting piece because there's a lot of things ongoing in industry developing bispecifics and bispecific repertoires, and it's not trivial actually to select the bispecifics which are developable. In our system, we can put different formats. We're not really limited to single-chain VHH. So in this case, there is a single chain on one chain, which is on the surface linked, and the other one, the VHH, is actually soluble produced. Of course, you can do this for one antibody, but we also did it for whole repertoires. And you can then select the ideal combination, looking at binding of both targets and also developability at the same time in flow cytometry. Also, FC fusions have been made, and also you can do the same actually to select for CAR T cells, for the ones that actually are good displaying and to get rid of the poor ones which have ionic signaling. For this, we actually use then URCAT cells and HEX cells to get there. And actually now we actually have requests from some clients to actually go beyond antibodies. And for example, if you want to develop a new flu vaccine, you can actually display other proteins on the surface and select actually the vaccine candidate using mammalian display. And then use that, for example, for an RNA vaccine preparation. So then I want to finish with some of the future ideas for platforms at Fair Journey. And I talked about these explorer concept, which we partly validated in Phaja, but now moving actually to validation of the mammalian display system, where we can shuffle actually these modules and optimize the antibodies. So we're going to show that the PD-1 and HER2 antibodies can be very quickly optimized using this system. We can also optimize just bispecifics in this way. And we also want to include, and we're busy starting with that, to use microfluidics technology. Because so far, we use mammalian display only, but to make a switchable system to go to functional screening, soluble screening. Because that's the holy grail everybody was looking for. Can you do very early functional screening on the single cell level so that you can quickly identify the clones that are potent, that are developable, and actually have the right function? And finally, we are a display company, so we use basically display technologies, but we've seen around many technologies and many people use immunization or, for example, just human donors disease material to select antibodies. Either directly plasma cells and use actually then function activity, but this is a bit limited because plasma cells are not that very stable. If you freeze them, so you have a limited window actually to do this functional screening. So therefore, actually, we actually are working now with plasma cells and memory B cells, the antigen-specific one, to set up a platform where we actually put them in special, let's say, droplets. And these droplets actually are semi-permeable. That means that all the reagents like primers and enzymes can go in, but the products that are made, the RNA and DNA, is too big to get out. In these droplets, we take the single cells, we link the heavy and light chain together, and we can do this for large repertoires of 10 to the 6, 10 to the 7, and then use our mammalian display system to actually then display them and select them. And we're working on a switchable system to actually again switch to the soluble expression on the single cell level, put them in droplets, and use actually a microfluidics device then to select the antibodies for binding, but also functional assays. So this is something we're working on, and I hope that I can report next year a bit more details on this. So in summary, we actually developed a semi-synthetic library, used basically combined phage display with our mammalian platform to select highly developable antibodies. Our mammalian display technology allows the selection of any antibody repertoires, so not limited to any format. And in the future, we want to use microfluidics and mammalian display to further select for functional antibodies, and also set up a B-cell platform to really directly go to the functional full-length antibodies in the discovery process. I would like to thank everybody from Fair Journey for the support, all the research teams for the support, but in particular, the Explorer technology team, Emiliano Pavoni, Raquel Pino, and Joanna Branco for all the hard work they did the last 5 months on validating this Explorer library, and also the B-cell technology team headed by Manuja Hatch, and 2 members, Denise and Lubna, who just joined a few months ago. And also would like to thank Peter Slavny from our Cambridge side and Tariq Kadur for the really stimulating discussion and help. And I want to finish with also thanking John McCafferty, who hopefully is also here, who actually the initiator of this mammalian display technology and also the designer of the Explorer technology for all the work and intellectual input. And I would like to thank you for your attention.